Okay, it's a great pleasure to introduce Professor Frank Pacard from École Polytechnique. We all know him, he's a big friend of IMPA in Brazil. And he's going to talk about doubling construction for free boundary minimal surfaces in the three-ball.
Well, thank you. So I'd like to thank the organizers for giving me the opportunity to talk here. And so I will talk about some doubling construction for minimal and constant mean curvature surfaces. So to start with, I will give you an overview about what is what I mean by doubling construction, and then I will explain how this can be used to construct minimal surfaces in the three-ball that meet the boundary of the unit sphere at right angle. So the general framework is the following. So you take so lambda will be a minimal surface, let's say in a three-manifold, but also it works in a higher dimension. And so you assume that it is compact, oriented, and embedded, even though you can relax some of the hypotheses. But for the simplicity, I will assume all this. And so there is one definition that will come out, which is the fact that a minimal surface is non-degenerate. So what you do is that you compute, once you have lambda, you compute the Jacobi operator, which has appeared already in many talks. And this is just the Laplacian on lambda plus the square norm of the second fundamental form. And then there is the Ricci tensor applied twice to the normal vector. And so you say that lambda is non-degenerate if this operator here has no non-trivial kernel. So in particular, since it is elliptic and we are in a compact surface, what it will mean is that having no kernel, it will imply that it can be inverted. Okay. Now, so the idea is that once you have a minimal surface sitting in your three-manifold, then you can apply the implicit function. And if you assume that it is non-degenerate, then what you can do is that you can apply the implicit function theorem and produce surfaces that are nearby and are parameterized by their mean curvature. So the statement which is completely obvious is the fact that close to lambda, you will have a one-parameter family of surfaces which have constant mean curvature, let's say, equal to epsilon, and epsilon is a small parameter, so close to 0. And moreover, this surface, so lambda epsilon, is a normal graph over lambda, and you know exactly what is going on because the function, it's a normal graph for some function, and this function has a nice expansion in powers of epsilon, so it starts like epsilon times a function psi plus something which is much smaller, like epsilon squared. And what is psi? So psi is a solution of this PD here. So as I said, since you assume that lambda is non-degenerate, you can always cook up psi, and then you have uniqueness of psi, and this gives you basically the shape of the surface which are which have constant mean curvature small and close to lambda. Okay, so what is the doubling construction? So the doubling construction is the following question. Can you perform a connected sum between two copies of so lambda epsilon and lambda minus epsilon to produce new constant mean curvature surfaces? So maybe I should draw a picture here. So it is a very schematic picture because my ability to draw a picture in dimension 3 is not so good. So let's assume that this straight line pictures lambda. Okay, so this is the minimal surface you start with. And then what you have is that close to lambda, thanks to the implicit function theorem, you have two new, constant mean curvature surface. So one, let's say, is like this. So this will be lambda epsilon. And then you find out that there is another one which is like that, let's say. And in fact, they are not completely. So this one is lambda minus epsilon. So this one has mean curvature epsilon, and this one has mean curvature minus epsilon. But what you have to understand is that all these surfaces, they are oriented, and the orientation is taken in this way. Okay, so here there is a new normal, and here the normal vector field is like this. So what you do is that, so this one has mean curvature epsilon, and this one has mean curvature minus epsilon. But what you do is that if you reverse the orientation, then this one turns out to have mean curvature epsilon also. And so the question is whether you can connect the upper one and the lower one through some bridge like this. And so that the connected sum has mean curvature is equal to, let's say, epsilon. And you see that the orientation fits so that this is possible. Okay, so this is the question. So in other words, what you have done, so if this is possible, what you will do is that you will create a family of surfaces which have, it's okay. The family of surfaces which have mean curvature very small, and what happens is that as the mean curvature tends to 0, you converge away from points to a double copy of lambda. Okay, so in some sense, what you have to keep in mind is that you take 2 copies of lambda, you push them slightly apart, and then you try to connect them by small necks. So this can be done, and so this is a work of mine and a student. So this can be done, but unfortunately, this cannot be done at any point. So what you have to do is that, remember there is this function psi, which solved the Jacobi operator applied to psi was equal to 1. And what you have to do, you can perform exactly this connected sum precisely at points which are critical points of the function psi, and which are not in the 0 set of psi. So in particular, what I've drawn here cannot be done. And so the place where you can do the connected sum has to be a critical point of the function psi. And you see that basically this guy here is the graph, is roughly speaking the graph of epsilon times the function psi. So in other words, the connected sum has to take place somewhere here. So this means that there are very few, in fact there are not so many places where you can perform this connected sum. So one interesting thing is that if the function psi does not change sign, then you see that the surface lambda epsilon will be on one side of lambda and the other one on the other side of lambda. And then one can check that the connected sum you get is in fact produces constant mean curvature surfaces which are embedded. Okay, so here I will give an idea of the proof, and the proof is rather technical at some point, but the idea is just a formal construction. So I hope that everybody will be able to follow. And and the idea is the following. So what you have to do first is that you have to perturb this surface here, which has mean curvature equal to epsilon. And the way to perturb it is by taking the graph over this surface here for a function which corresponds to Green's function associated to the Jacobi operator. So what you do is that for simplicity, let's assume that psi at the point P is equal to 0, and that we want, so the point P is here, and that we want to perform a connected sum, let's say at this point. So what you do is that you cook up the function gamma, which is nothing but Green's function. So you see that on the right-hand side, there is a multiple of a Dirac mass at the point P. And you can check that, so first of all, it is well defined. And in normal coordinates at P, you can check that the function gamma looks like minus the log of mod x. Okay, and so the idea is that instead of considering so what you can do is you can start with a surface which would be the normal graph over lambda for this function here. And you see that this function involves 2 parameters. There is a parameter epsilon, and the parameter epsilon will be exactly the mean curvature we try to prescribe. And there is another parameter which is called eta, and which is a bit mysterious for the time being. But what you can, so you see that you have 2 graphs. So the first graph will be so maybe I can erase this. I will erase this one here, and that one there. Okay, and so the picture is more like this. So what you have is that this one here is the graph of epsilon times psi plus eta times gamma. So I hope that I hope that the signs are correct, but in fact, I think that the signs are wrong. But you know, it's let's see. No, yeah, I think that the sign here. I corrected the sign this morning here, and the sign here is wrong. But let me tell you what. Yeah. So basically, what you have is that you should have a minus here. But let me draw exactly what will happen. Is like this, and here what I have is that I have the graph of minus epsilon psi plus eta times gamma. Okay, and so let's assume that the point P I choose is this one, and what the graph looks like. The graph looks like something like this here. So, and here the graph looks like something like that. Okay, so that's the reason why the signs are wrong. Okay, so you cannot continue the graph until you approach very much P, but basically you have two graphs like this. And the idea is you try to insert here a rescaled copy of a small catenoid in such a way that it will match exactly the asymptotics you have created here. So, so one important feature is that if you compute the mean curvature of this here and you're not too close to the point P, then you see that the mean curvature is almost equal to epsilon. And this uses the fact that away from the singularity, the function gamma satisfies the left-hand side is equal to 0 away from P. So once you are here, so what you do is that you look at the catenoid in Euclidean space. So the usual parametrization of the catenoid in Euclidean space is this one. And what you do is that you change coordinates, so that the first two coordinates, you call them x. And you find out that with these coordinates, the upper hand of the catenoid, a vertical catenoid, can be described as the vertical graph of this function here. So here there is a log term, and also there is constant c. And you see that as mod x tends to infinity, this becomes smaller and smaller. So the value of the constant c doesn't matter too much in the construction, as you will see. So what is very important is that the upper end of the catenoid looks like the graph of the log function. And so now what you do, so what you do is that you compare, so what you do is that you can take the catenoid and then you can scale it by a factor eta, scale it down by a factor eta, and then you can look at the upper end of this scaled down catenoid, and with a change of variable you see that the upper half, the upper end of the scaled down catenoid is the graph of a function that can be expanded like this as mod x tends to infinity. And now, so now you see that in geodesic normal coordinates, then this function here can be expanded exactly this way. So here there is a sign mistake, but here there is not. And so if you compare the two expansions here, you find out that well, the two graphs, they look like a multiple of the log of the mod x. And then there is a constant. And here this constant is just epsilon times the value of psi at the point P, while here the constant is like minus eta log eta. So this tells you that, at least from a formal point of view, what you have to do is that you have to choose this mysterious constant eta in such a way that this equality is fulfilled. So as epsilon tends to 0, you see that epsilon is the mean curvature we try to prescribe. Then this gives you the value of eta. And roughly speaking also, what it does is that it gives you the, so basically this size here is like epsilon, and so it is like a size minus eta log eta. Okay, so this is how it works, and so once you have understood this is just formal computation that helps you to design an approximate solution to the problem, and then one needs to perturb this to produce a constant mean curvature surface. So you see that here there is something weird, because in this formal computation, in this formal construction, I never used the fact that the point P needed to be a critical point of the function psi. Now, let me try to explain in a few words why one needs P to be chosen to be a critical point of the function psi. So in some sense, this is quite, from the physics point of view, on this drawing here, this is rather natural, because you see that if you want to attach somehow, you have this surface here that has a slope, And if you want to attach a catenoid, what will happen here is that you will attach the catenoid in such a way that the axis of the catenoid will be bent, will use the bend of the slope here of the graph. And then the axis of the catenoid will have to be oriented this way. But if you perform exactly the same job upstairs, then you can see that the axis of the catenoid you try to attach also will be bent. Okay, so in some sense, what you would have to do is that to perform the connected sum, you would have to find a catenoid which has two ends. One of the ends will be like this, okay, and the other end would be like that. Okay, so one doesn't know what is in the middle here, and in fact, this is known not to exist. So in some sense, what you have to do is that you have to put yourself in the position where the catenoid will, the axis of the catenoid matches exactly from the upper surface and the lower surface. Okay, so this is from, let's say, from the geometric point of view. But then there is a more complicated and PD question behind this, but this becomes very technical. Okay, so now let's give two examples. So first of all, what you can start is that you can start with a sphere S2 in S3, so a great sphere. So in this case, the Jacobi operator is given by this, and unfortunately, this one has a non-trivial kernel. Okay, these are given by coordinates function. So unfortunately, you cannot apply the theorem to this example here. But nevertheless, what you can do is that you can work with equivariantly. So what you can do is that you can try to prescribe so you see that in this case, in fact, the function psi is equal to 1. And so all points are critical points. And in the previous theorem, I asked that the points where the connected sum should take place have to be non-degenerate critical point of psi. But here, all points are critical points of psi and are degenerate. So you cannot apply directly the result. But what you can do is that you can work equivariantly. So what you do is you can try to build constant mean curvature surfaces which have some discrete symmetry. Okay, and in fact, you can do it. So for example, what you can do is that you can try to, so you take two copies of the sphere S2. And so what you do is that you put one slightly above and the other one slightly below the great sphere. And so they would have mean curvature small but non-zero. And then you can try to connect them to perform a connected sum along at many points which are evenly spaced along a great circle. And in fact, you have enough symmetry to kill the kernel of the operator here. And precisely the result I stated works in an equivariant setting. So now, another example, which is the Clifford torus, which has already been used in the previous talks, so the Clifford torus in S3 is a minimal surface, and this time the Jacobi operator reads twice the Laplacian plus 2, and this is the flat Laplacian. So this is the Laplacian on R2, and what I've done is that I've parametrized the torus by two circles. So 0 to pi will be the first variable, and there is a second variable belonging to 0 to pi. And so again, you can see that this operator here has non-trivial kernel, so you cannot apply directly the result I stated. However, what you can try to do, again, is to work equivariantly. And this works pretty well. So what you have to do is, so this is a result I obtained with Adrian Butcher. So if you picture the torus, so if you picture the torus as a square, so here 2 pi and 2 pi, so I have two angles, theta 2 and theta 1. And so you parameterize the torus like this, and what you have to do is that you can take a lattice in R2, so that contains many points. Okay, so you need to have many points. So I'm not very good at drawing periodic lattices in the plane, but what you have to do is that you have to take many points, and in fact on the sphere you can see that you can pass. So if this is a regular lattice, then you can arrange this in such a way that this corresponds to a discrete group of symmetry of the sphere. And working equivalently, if you have enough points in your lattice, then you can do a doubling of the Clifford torus to obtain constant mean curvature surfaces with small mean curvature, which look like the two copies of the Clifford torus which are connected at the points of the lattice by small cathenoidal necks. So again, this is just nothing but the result I stated before, written in an equivalent way to get rid of the fact that the operator you start with, the Jacobi operator, has non-trivial kernel. So I think more interesting is this work by Capules and Young. It's not very well known, probably published like 4 or 5 years ago. And what they have done is that they have done exactly the same way, same thing. So they have done the doubling of the Clifford torus. But what they have done is that they perform the connected sum at a very large number of points. Okay, so what they do is that they take in fact, in their case, they take a lattice which is a regular lattice, and what they do is that they try to do the connected sum, and okay, so like this. I'm not going to draw all the points, but the key idea is that this distance here is 2 pi over n, and n is an integer which is supposed to be very large. Okay, so here there is no continuous parameter, there is a discrete parameter, and what they claim is that if the number n is large enough, and then if you do this doubling construction, then what you end up with is not a constant mean curvature surface, but a minimal surface. So let me try to explain where this condition here enters in the construction. So again, what you have to do is that you have to work with Green's function. And this time, what I'm going to do is that I'm going to, so what would be gamma? Gamma will be a harmonic function. And this function has the property that it has a singularity at each point of this lattice here. So what you can check is that, so in some sense, what I have done is that I've taken the so gamma solves Laplacian gamma is equal minus 2 pi the sum of Dirac mass at all the points in the lattice, which is here in lattice. Okay, so gamma depends on the parameter n, and in fact there is no. What you can do is that gamma can be expanded in a series like this, and what is important in this thing is that gamma starts with a constant which is minus n squared over 2 pi, and then you have a sum of functions which can be defined inductively, and the most important one is the first one, which is G0. Okay, so gamma looks like minus n squared over 2 pi plus G0 plus 1 over n squared times G1 plus 1 over n to the 4 times G2 and so on. And the key point is that G0 is singular and it has a log term singularity, while starting from G1, all the other function G are bounded. So roughly speaking, what you have is that gamma is this large negative constant plus a function that looks like log plus a function which is in fact bounded uniformly as small n tends to infinity. So this is the idea. So here what you do is that so here there should be over n. I'm sorry. So gammas of this equation here in a small with periodic boundary condition in, let's say, in a small torus here. And what is important for us is that gamma gets an expansion of this form. And what is crucial in this expansion here is that there is a log term, and here there is this term which is very large. So if you picture now the graph of the function gamma, so this would be like this. So it's quite difficult to picture, but so as usual, I will assume that the minimal surface I start with, which is the Clifford torus, is just this straight line, And what I do is that I multiply, so this is the Clifford torus. And then what I do is that I look at the graph of epsilon times gamma. Okay, and so if you look at the graph of epsilon times gamma, then again there is a, I'm sorry, all my signs are wrong, but you know, this is, yeah. I'm sorry, I changed all the signs and now they are all wrong. So here there is a minus. And so what you have is that if you look at the graph of epsilon gamma, so epsilon gamma, then what happens is that this here, what you have is you have the ground which is minus epsilon times n squared over 2 pi. And then you have a graph over this. Yeah. So you have the graph over this will have singularities evenly spaced, like this, log type singularities, and which are evenly spaced, and the distance between two singularity is like 2 pi over n, so it's 1 over n. Okay, so the effect, so you see that the effect of putting a lot of singularities here, what happens is that this constant here is quite large, and even multiplied by gamma, it lowers a bit this, and then you will have room to, so if you compute here the graph of minus epsilon gamma, it will be like this. So this is the normal graph over the torus. And then what you have to do is that you have to insert the catenoid exactly as I did before. And formal computation using the asymptotics of the rescale catenoids tells you that, in fact, the parameter epsilon and the integer n should be related by this formula here. So roughly speaking, it tells you that what you have to play with is the number of points of the lattice. And if you take the number of points of the lattice large enough and you fix it, then there is a unique parameter epsilon, which is given by this formula, in such a way that you will be able to insert small catenoids here and then to perturb to obtain a minimal surface. So, so this is the this is a doubling construction which is slightly more elaborate than the previous one, because what you have to do is that you have to play with the number of singularities of this function gamma you start with. Okay, so how does it how can this be used to construct free boundary minimal surfaces in a three-ball? So there is a recent result by Elena Fraser and Rick Shane that has been published this year that says that there exist free boundary minimal surfaces in the three-ball which have genus 0 and n boundary components, and the limit of these minimal surfaces as n tends to infinity is a double disk. So a free boundary minimal surface is, so these are surfaces that are embedded in the three-ball, and they have the property that they have a boundary on the two-sphere. They touch the boundary on the two-sphere, and they touch it in an orthogonal way. So, so obviously there are some examples. So what you can do is that you can start with the intersection of the three-ball with a plane, and this gives you a two-disk, and this two-disk meets the boundary of the three-ball at right angle. But also there is a special catenoid which has already been mentioned in a previous talk. That is so this special catenoid. So you take the catenoid and you scale it by a factor, let's say alpha, and then there is a special value of alpha in such a way that the catenoid will meet the boundary of the three-ball orthogonally. So. So these are two very well-known solution of the free boundary minimal surface problem in the three-ball, and what they have obtained here is something which is slightly more complicated and which can be thought as so we will see in the next slide what it looks like. Okay, so. With Abigail Follas, what we have obtained is that we have obtained a new construction of the minimal surface, free boundary minimal surface, which have been obtained by Elena Fraser and Rick Shane. But also we have obtained surfaces which are not congruent, which are slightly different. So let me try to give an idea of how to construct these. So here, let's assume that I have the 3 ball here, and here I have the disk D2, and this is a solution of the problem here. And what you can do is that you can perturb D2 in such a way that you will produce surfaces which have constant mean curvature, small, close to 0, but which meet the boundary at right angle. And so you have spherical caps like this that meet the boundary at right angle. And this one here have small mean curvature. Okay? So eventually what you could do is you could do connected sum here, but this is not what we want to do. But the idea is to play exactly the same game as in the result of Capuleas and Young, putting a lot of necks in such a way that you don't get constant mean curvature object, but you get a minimal surface. And the idea here is to look at along the boundary and to connect two. So what you do is that you take 2 disks which are parallel to the unit disk here. So one will be there, and the other one will be below. So obviously they don't meet the boundary of the 3 ball at right angle anymore. And what you are going to do is that you are going to connect them here using half catenoids which are evenly spaced. Okay, so maybe it is better to see the view from above. And see, if I were to see the view from above, I would have the surface I would obtain would look like this. And so, like that. Okay, and what is it? So what I do is that I take a catenoid which has a vertical axis, I cut it in 2, so this gives me a half catenoid. And what I do is that I try to glue this catenoid on the boundary of the 3 ball, and then perform, let's say, a connected sum between this disk here and that one using a lot of half catenoids like this, which are evenly spaced along the boundary of the 3 ball. So here the parameter is again the number of half catenoids you put. So this angle will be 2 pi divided by n, and n will be very large. But also what you can do is that you can do exactly, as we will see, you can do exactly the same construction. But also here, what you can do is that you can put in the middle of your construction one catenoidal neck. And so this would produce a new surface. So as you see, this surface has a lot of symmetry, has a dihedral symmetry. Right, and as in the result by Capuleas and Young, the parameter here is the number n. So here it is slightly more complicated, and so what you have to do is that you have to parameterize the 3 ball in a reasonable way. And so what we have chosen is this parameterization here. So in fact, Z belongs to the unit disk and T belongs to R. And what happens is that Z is related to the parameter S and theta by this formula here. But in any case, so what you have is that in this parameterization here, the surface corresponding to T equal constant is a constant mean curvature surface, which is in fact a piece of a spherical cap. Okay, so once you have done this in these very special coordinates, you can compute the linearized mean curvature operator. So you have to be a bit careful. The linearized mean curvature operator is not exactly the Jacobi operator. You see that let's say we start with the unit disk. So the Jacobi operator about the unit disk is just the Laplacian on the flat Laplacian. But what you have is that you find out that this is exactly this, because the vector field d over dt does not have norm 1 all the time when you compute it along d2. So the operator we obtain is not the Jacobi, but it's conjugate to the Jacobi, and there is this factor that comes in. But you see that this factor is not a big deal because it is always positive and smooth and so on. So that's it. So once you are here, so this time I hope that the signs are correct. I was confused in the sign of a log, but it's okay. So this time what you can do is that you can construct two functions. So the first function will be called gamma twiddle. And gamma twiddle has the property that it solves the linearized operator is equal to 0. It has 0 Neumann data. And also what it does, it has a log type singularity at the origin. So in some sense, if you take the graph of epsilon times gamma twiddle, then you find out that you have a nice surface that also almost meets the boundary of the sphere, of the boundary of the ball at right angle, and whose mean curvature is extremely close to 0. Now there is another function which is called gamma n, and this function gamma n is the one that it is a harmonic function, and it has the property that it has log type singularities at all the nth root of unity. So there is, in fact, it is not very hard to check that this gamma n is this time completely explicit. So the fact that it is explicit is not so important. But again, what you have is that as n tends to infinity, one can see that gamma n times starts with a large constant, n over 2, and then there will be a log term singularity, and then you will find that there are garbage which are bounded independently of n. So in particular, you see that this function gamma n is cooked up in such a way that it solves that the linearized operator applied to gamma n is equal to 0, and it has 0 Neumann data. So basically, this gamma n plays the role of Green's function in the previous works, and the function gamma twiddle exactly plays the role of Green's function in the previous work because it has interior singularity. Now, finally, what you do is that you construct, you take the normal graph of epsilon times gamma n plus gamma twiddle, and so you see that you will find this will be a surface which is not a minimal surface, but which has mean curvature extremely close to 0, like epsilon square. And then you find out this time that so what you do is that this function here will produce a graph that has a lot of singularities like this, and maybe a singularity inside close to the origin, and then you try to insert rescaled, half rescaled catenoid in between the upper version and the lower one, and you find out that to do so there will be a relation between the number n, which is the number of punctures you have on the boundary, and this parameter epsilon. So in the case of the Clifford torus, there was basically log epsilon was like n squared, but here in this case log epsilon is like n. And once you have done this, then it becomes a bit technical. You have to do a perturbation argument, but there is no let's say geometry involved in the sense that you have done everything you could to try to find a good approximate solution, and then it's just technique to perturb it. So I will finish here, and the purpose of my talk was to try to make the difference and try to explain the two types of doubling construction: the one that would produce constant mean curvature surface with small mean curvature, and the one that would produce immediately minimal that will produce minimal surfaces. But here you see that the number of connected sum you have to perform is usually very, very large, and this is a discrete parameter you have to play with. So also it is a bit confusing in my talk because there is a continuous parameter which is epsilon, and if you come to think about it, it gives the impression that for all epsilon you get a minimal surface, but in fact this is not the case, because this parameter epsilon is in fact fixed by this equality here, so it is in fact a discrete parameter. So I will end up here, and thank you for your attention.